surface of P with another way to say it is that, so in particular, the inverse image of a point, a circle, a fiber of a point, is, once you add the knot itself, a cipher surface for the knot. And you might wonder, here's a quick quiz. Why, how do you know from this that sigma CP is oriented surface?
Because it's embedded in R3 or S3.
You can embed
R3.
Mobius band embeds in R3.
Oh, that's probably,
I mean, I guess
we can
just use the tangent bundle of S1
Okay.
that sort of lifts to a choice of like normal everywhere.
Okay. So you just finish the argument. You're just taking having a well-defined normal.
Yeah. Okay. What's our definition of?
Oh, an oriented manifold is something we have a chosen orientation of the tangent space manifold. But yeah, I understand what you're saying. So yeah, so oriented submanifold, an oriented surface inside R3 or S3 is something that has a well-defined a choice of a normal direction. Right. So as long as you project, if you're projecting to S1, if this is a fibration has no singular points, no critical points, then take a gradient vector field, like a metric on S3 minus K, and then take a gradient like vector field for it, and that'll give you something that points left transverse to K everywhere, therefore well-defined normal direction for that oriented K. Okay, so I want to see the trefoil on this fiber, and so the way to construct a fibration is just to first take a cipher surface for it, and I'll draw it kind of as we did before. This is one of the ways to see the fibers. Another way is there's a purely algebraic way to see the fibers, namely there's a map from C2 to C, which has a singular point at the six inside. What is this a map? B is a polynomial map. In fact, it's the map Z1, Z2 goes to Z1 squared plus Z2 cubed. And then if you take let's call this G intersection 0, intersection with S3, it's a trefoil knot. So therefore, S3 minus G intersection 0 maps by G divided by 1G. That's 1, and you can show that that has no singularity. So that's a kind of purely algebraic way to see the effect. You have to compute something, you have to show that, compute the map, show the derivative of this map is number 0, and that works. But I want to see it when it's on. So what I want to do is I want to take in some sense, I want to sort of construct a circular Morse function on the complement so that the cipher surface is regularly set. And then, and that's, so first I'm going to take the cipher surface cross element. So step 1, that's this. Step 1, sigma, cipher surface. Okay. And then 2, consider 2 to the neighborhood. This 1 cross sigma. we really should be working in, we're gonna think of the cyclic surface as, I'm gonna work everything in the two neighborhood of K, actually. So I can think of, I'm gonna think of the cyclic surface as being outside that two neighborhood. So this would be contained in S3 minus the neighborhood of K. So, you know, the idea is that how is it going to hit the boundary here? It's going to hit the boundary, you know, here's, so I want the original cyclic surface to be 0 cross sigma. And then I'm going to thicken it up a little bit along the, this would be say -1 cross sigma here, and then 1 cross sigma, something like that. Do you understand the picture? We just thicken up a little bit, but in such a way that it meets the boundary, nicely. Okay, so, okay, and then I want to consider the complement of that, right? And then let's look at minus K minus sigma. And because, you know, so we're going to try to construct a fibration. So we can, you know, our fibration first is going to be, so I should, here, 2.5 is define F. Maybe I should call it -1/2. Anyway, F minus 1 cross sigma to be just -1. One. So parallel copies of sigma are going to be your level sets. I guess my S1 is going to be -2 or something with n points. So now I need to extend. So now extend F to, let's give a name to this. Call this. X. Then extend F to X. But we want to, the point is X now kind of is special. It has a special, you know, I'm doing the usual geometric topologist thing when I take the complement of something, I leave the boundary in there. Right? So X is actually a cobordism from, see what's the boundary of X? The boundary of X is, part of it is sort of half of the boundary of the tubular neighborhood, and half of it is, the other half of it is one copy of sigma, and the other copy of sigma. And this, the part on the boundary of nu, this tubular neighborhood, is just a product. So I want to think of X as being, it's a coordinate from, doesn't matter, let's say from, actually carefully, 1 cross sigma to -1 cross sigma. So I want to think about it in the following way. This is a purely schematic picture. I've taken, here's my K, just a pair of points, right? Here's my tubular neighborhood of K. Here's sigma. Here's the -1 cross sigma, so -1 cross sigma. And then the complement X is everything outside. X. Think of X as being a, if the coordinate direction for this neighborhood went that way, I just want 1 cross sigma was coordinate from here to here, and then X should, if I want to construct a vibration going the rest of the way, actually, which is the bottom of it being 1 cross sigma, and the top of it being -1 cross sigma. And if we can show that this coordinate is a product, then we're fine, right? So, try to show. x is also diffeomorphic to these products. Respecting this cobordism structure. And so let's look carefully at what x is in this case. But first we want to understand thinking of sigma. So the first, warm-up exercise. I don't know if this ever surprised you the first time you heard this, but what I always thought was a strange fact the first time I was doing topology is that if I take a disk minus two disks versus a once punctured torus, for example, and cross both of them with the interval, they're diffeomorphic. Because this is that. And once you cross this with an interval, it's just cross the interval, it's just a ball with two one ends attached to it. And this is a ball. You cross this one, it's a ball with two one ends attached. To whether it's attached this way or that way, if it's in 3 dimensions, it doesn't matter how the feet are attached, right? So
You can also see like
I don't know when you
other
first learned
sides.
that.
The punctured torus like curls back into itself.
Oh, right,
And
yeah.
it goes
Yeah,
around.
if you just think of this here, you can sort of see it.
It's just like a different embedding.
Right. Anyway, I found that dramatic first time I saw it. But so the point is, well, the first thing to check here is that this cipher surface is actually a punctured torus for the triflow. And maybe the easiest way to see it is to see that abstractly it's built out of. Well, I don't know. So you just compute the other characteristics, it's not that hard, but we can also just thicken it up and see quite directly when we thicken it up. Well, it has the big difference between these two surfaces, the disk with two holes taken out versus the punctured torus is the number of boundary components. And you lose those number of boundary components, the distinction between those when you cross with the surface. But so anyway, it's not hard to see that this is that this green thing is a Morse punctured torus. It's not embedded in the standard way. And then when you thicken it up, it's even easier to see that you get just a genus 2 handle. And the way we've got when I thicken it up, what's going to happen since this outer disk I made pass through infinity, right? Then I'm going to have thicken it up. I'm just going to have the complement of the ball. Right, so sort of draw a picture of that. So actually, I'm going to try to draw directly a picture of x. Right? So x is going to be inside. First of all, it's going to be inside the ball. Because when I thicken up the screen surface outside, including infinity, it thickens up to be a ball. And now, everywhere where I've got thickened bits of green, it's like drilling a hole out of this ball, right? In particular, I've got, I thicken up this green thing here, and that becomes a. So this is, out here, I've got sigma, here I've got a little bit of minus 1 plus sigma. And then I've got 3 tubes structure, right? Because I've got this twisted strip going through here, but it's thickened up. So a thickened up twisted strip is just a one end line. From there, and here. See what happens, right? So in particular, we actually draw the knot on here, right? Or maybe better yet, we can draw the boundary. Well, we really want to draw. So x now is this stuff. And now I don't really need to draw, I don't really need to draw the whole ball outside. Another way to see what's happening with x is that I've got a blob here, blob here, blob here, okay? And let's see this right. no, sorry, a better way to say it is, you've got a blob in the front and a blob in the back, and then a tunnel through here, a tunnel through here, and a tunnel through here. So, the complement, if I take a concentric sphere and I drill holes in it, it's the same thing as take two blobs here, connecting them by two back. So then finally I want to sort of draw, I want to redraw that picture the following way. Draw X. So how does that picture supposed to correspond to that picture? This, I guess this picture sits here like this. These three pillars here run right through here, here, and here. Okay, and then this, say, is in the back, and the top part is in the front. Can you visualize that? So in other words, it's the front half of this drill that thing, the back half, and the pillar. But the point is now we can sort of see what's going on with. I want to draw. I want. That's a nice picture of X, but I don't see it as a coordinate. That's the important thing. So now I need to see as a coordinate. In other words, I need to see how the boundary of it is divided up into two parts, product of two. And so there we have to take this green thing and see what it does going through here. Remember, it's about the way the green thing intersects here, so it goes through the back, and then it goes around the back, goes up. This goes here, just from the front, goes up. So we want to sort of see what's happening here, and I claim that up to possibly changing all my crosses from right to left, the boundary seems to this. I just switched left trefoils for right trefoils for you. Okay. I mean, maybe the better way, the point is, if you look at, I guess actually what really matters here is looking at, do that right. Maybe I should try to draw it first here. And as you go in, these two strands do a half twist, right? So I'm going to go there, and I'm going to go there. And similarly this. But now the point is, if you also look at okay, so if we look at the maybe I'm trying to make this too complicated too quickly. I'm trying to jump too many steps in this picture. We want to sort of displace some of this to the front, right? Because we got a front blob. The thing is a front blob and a back blob, right? So let's say we displace this curve to the front, and these curves to the back a little bit. So these three curves will end up being these three arcs, 1, 2, 3, okay? And these three arcs here end up being these three arcs, 1, 2, 3, right? And so I just need to argue that in connecting this arc, in going from here to here, as I go through the thing, I also just see a half twist. And so I hope that's clear enough here. So I see that half twist going through here. This becomes, it's really these two strands that twist around. So I've got, and so now the question is, well, let's figure out where is -1 cross, let's draw one of these two parts on here. And if I draw, let's say, it doesn't, I mean, this curve should divide the boundary of this into two parts. And it's, stuff around the back. I'm not going to draw. Okay. So at least that's good. At least the curve, it doesn't end up having only one side. So there's, let me put this up around the back. So what we need to see, what we really need to do is see is there a diffeomorphism from this solid handle body to -1, to an interval across a punctured torus, taking the orange part of the boundary to one half and the other part to the other half of the boundary, right? And that's not, we'll do an example where you see that that's not totally obvious. I mean, it's not totally, I don't know if it's totally obvious to you, not how you would argue that.
Could you say that one more time?
It does, I'm gonna write it down. Okay? So the question is, does there exist diffeomorphism from X to in 0, 1 across sigma, it should be the same sigma, such that orange goes to 0 across sigma, and then 1 orange on boundary goes to 1 across sigma. Because the point is that.
So you're being sort of a little loose about like a little color around the curve.
Oh yeah, good point. Yeah, I mean, you're right. Really, I should think of there being 4 parts, but and I should really think of this thing as having corners, right? And that's exactly what I'm being loose about. But as you can imagine, it doesn't really.
Sure. Like, obviously, that curve has like a trivial.
Exactly.
neighborhood.
Make it very, very small, right? So I'm really gonna think of it as a conversion from this orange stuff to the not orange stuff, and then this is gonna be the sides of the conversion, right? And right, so obviously if orange and not orange fill up the entire boundary, 0 across sigma, 1 across sigma don't fill up the entire boundary, so there's something you understand. And so I don't know, any ideas for how you could decide if such a thing exists or show? I mean, I think such a thing does exist in this case. I mean,
We can do a sanity check by just computing other characteristics, because I think
That's
it should be a punctured torus, or at least have the same other characteristics.
Well, okay, so first of all, X itself, we know is diffeomorphic to 0, 1, sigma equals this, right? X is diffeomorphic to that, that's fine, right? But it's a relative question. We've got a particular decomposition of the boundary into 2 parts. And then when you take this cross sigma, where you get this cross interval, where you get a particular decomposition into 2 parts. And the question is, how can you decide if the way that this boundary is decomposed into 2 parts is consistent with? And the point is there are many different diffeomorphisms from this solid handle body to this cross 0, 1. So in other words, what we want it to look like is, we want it to look like this. Well, actually, let's try and draw what it should look like. It should look like, maybe, okay. Well, we should have a, I guess I don't know why I'm trying to draw it. You can imagine this thing thinking up. Right? It's a kind of a funny picture when you draw. If you draw the normal handle body, if you thicken this up and then carry out the diffuse Morse we just talked about from this to this, and what you want to do is look at this curve. It runs around there once, and look at what that looks like over here, and then reset and match up with this. Okay, but there's a sort of a maybe slightly easier way to do it, which is to to say, can we so can we just realize this? So what I want to propose doing is trying to build this diffeomorphism little by little. Okay, let's first try to build that diffeomorphism along some thickened up disks. Yes. Okay, so let's first, so we're gonna, if I take a thickened up disk here, let's say, and a thickened up disk here inside, right? Then, so let's call this, here I've got call this A for painless, right? And notice that on just if I just zero in on the annulus, just zero in on the thickened up disk, that everything looks pretty good because I see the green curve, say intersecting something like that, right? And then the orange is one side or the other of that, and top and bottom doesn't matter, right? And so I can then say, great, this is just, I want to say that this is diffeomorphic to just a rectangle across an interval. Right? So this is the green stuff here, right? I feel like that's the green stuff there. Right, so in other words, I'm going to construct this product structure. So then the point is, if I want to then see the boundary of this, so what I really want to keep track of is the boundary of the center. I'm trying to make everything a product. So here. So I'm going to another way to say what I want to do is I want to cut out a solid disk, thickened up disk here, and when I remove that thickened up disk, so I'm taking this thickened up disk and I'm realizing it as the orange thing intersected with the boundary here across it. Okay, so for those of you in the bigger research group, are all three of you in that?
The
The contact coordinates thing, yeah.
Yeah.
This is sort of similar. This is, have you talked about sutured, they are sutured. Okay. All right, so what am I trying to say? Let's go here. I claim that, and I claim there exists a diffeomorphism from this thickened up disk to a rectangle cross interval in such a way that the orange part of the boundary of this thickened up disk goes to the rectangle across 0, and the other part goes to the rectangle across 1. Okay, that's sort of clear. It's just, and the key thing there is that the green curve passes through here twice. That's all. It's 2 components of the green curve there. That's it. Right? And so now I want to extend. So that's going. These are going to be 2 parts of the this diffeomorphism. Now I want to see what's left after I've done it. So in order to see what's left, what I should do is remove those and see what I have. And so when I remove those, ball. the crucial thing is what happens to the, what happens on the green curve on the boundary of the ball, right? So I'll get a ball.
How are you connecting?
That's what we have to figure out. The green curves again. In the end, there's not going to be much to this argument. This is supposed to go all the way around. It's there. Okay, so how are we connecting? Where's the orange stuff? Well, the point is we want to extend our product structure. We've already constructed a product structure on those picking up discs. Oops. We've already constructed this product structure with picking up discs, and now we've got the question is, can we extend that product structure to the can we extend that product structure to this solid ball? So this is a ball, drawn kind of funny, and now it's easy because we look at what this product structure did, and what part of the product structure do we see on these slices? We see just that the two ends are connected and the orange stuff ends across the middle. So it's just as simple as notice the product structure is exactly what it should be there. And so now the whole point is, here's this ball, and how many components, what do we have on the boundary of it? And so if you then you figure out that this, now funny things could have happened, right? You just cut across discs and connect to the endpoints, right? Funny things could have happened. You might have ended up with, say, several components of this green arc. But because when you turn it into a ball, look at it carefully, this is just one component because of some hard theorem in elementary topology about simple closed curves on spheres, right? It's a sphere with one component, so it separates a sphere. It's a circle with one component. The sphere, so it separates it into two components, and therefore the product structure will extend. That's it. So it's hard to actually see the vibration, but there is this product structure. And so now we should try to work towards an example where this doesn't work. See something not true.
So we haven't talked about like suture homology or anything in Gordon's
No.
class.
Okay.
But we're doing like sort of exactly this kind of argument.
Right, exactly. So this is an example of what's called a sutured three-manifold. This surface with a solid handle body with some number of boundary components, some number of curves on its boundary, dividing the boundary into two parts.
Yeah.
Okay. Another way to say what a sutured three-manifold is, it's a coordinate with sides from some surface to another surface.
Like we're just doing it as
Yeah.
dividing curves as
That's
contact
right.
structures
Yeah,
and then
exactly.
trying to classify the contact structures.
So this is not an unfamiliar type of argument. Okay, so actually, this is sort of in some sense, more profitable. In some sense, we could have started with that picture of trefoil. Let's see if we can figure out well, no way to say this, but let's first see if we can figure out how far we can sort of generalize the trefoil and still be fibered. So in some sense, what was useful was to start with a picture of the trefoil sitting on this GS2 surface, right? And so we started with the trefoil.
Could you start with like the curve on the sphere? And then pick some number of disks that,
Yeah, I
like,
guess you
only
could do
cross
that.
it
Right.
once.
That's true.
and then
connect
just
them.
like glue them all up, and like,
That's true.
sort of no matter what you do, you're not gonna.
Well, you want to make sure that complement. See, this is now you're going to build. You want to have two things happening, right?
Oh, because you got to twist somehow. I see.
We got to this picture after we got to this picture after we had already known that the other half was a product, right? So this is sort of our picture, and there's an obvious ciphered surface here. That was not the ciphered surface we used. So in some sense, what really the point was that the cipher surface we used was, you know, another way to say it is in this picture you can kind of just see a different cipher surface here. And then it's, in a sense, maybe we could have made this argument even quicker, easier. This cipher surface thickens up to give that solid handle body. But that's not the cipher surface we started with. We got this other cipher surface, which is kind of hard to see in this picture. So, you know, for example, what if you put 3 half twists here? And so let's try to put some different number of half twists here and work the other way, right? So now we're going to use this as our starting point and try to work backwards. Right? We can see, so maybe this is pretty good because you can see the handle body here, and then the other handle body is a big outside ball with 2 one handles going through the tunnels here. Okay, so there's the complement. So the outside handle body is,
Handle body is just that surface thickened out.
one handle body is the surface thickened up. The complementary handle body is the complement of this big ball, it's a ball containing infinity, together with one handle going through here and one handle going through here. And we try to turn that inside out and draw this curve. So what I want to do is I want to change this picture now so that we put 3 twists in here to keep it as a knot. Or actually, more importantly, to keep it as an oriented surface. So now there's my red cipher surface for this green knot. Maybe I should make it not green, not red. But anyway, and now I want to try to, this is some other, I want to try to transfer that knot onto the boundary of this blue handle body. So we can by the way, knots that lie on something like this are called pretzel knots. Knots that lie on the surface of a GS2 handle body are called pretzel knots. It turns out a trefoil is a pretzel knot. And a pretzel knot is determined just by three numbers, how many twists you do and then across each pillar. So we're sort of going to investigate fiberedness of some pretzel knots. And so now if I draw, and imagine now sort of moving this ball down, making it small, moving off of infinity. A little ball with rings attached. Okay. And the green curve now is the green curve D. It's going to be, it's going to go, that way. Point is, it's going to go over each of those handles in a funny way. This is what's hard to picture, is how it. So one way to understand what it does when it goes over this handle, right, is to first of all count the number of times it's going to intersect a meridian for that handle. And it's going to, so we want to probably imagine that when you're going in, so this is in the front. We want to imagine that this is in the back and that's in the front. So here you're coming from the front and you're going through, here in the back. Here you're in the front, back. So what I want to do is try to draw a meridian for this post going through here and count points of intersection. So here we're going from the front to the back, front to the back, front to the back, so it's sort of hit one point there, point there, point there, point there, front to the back, and then here it's getting from the front to the back. The picture's going back a bit. What I claim is that it looks like, I'm just trying to draw it, it looks like this. I want to take this picture and turn 90 degrees, right? And say front comes up, right? Then we're going to have 1, 2, 3, 4 points where it crosses. And I'll try to go all in front, right? And then we have 4 strands coming through here, and then so. Just worked out in my office earlier. It's hard to do this. So I should draw this picture. I should be a little more careful as to what's up and what's down. And so let's say this is front. What am I trying to do? You might see it better than me, but let's try to salvage this argument, this picture. First thing before I flood it too much more, do you understand the problem that I'm trying to do right now? I'm trying to redraw.
What is that?
I'm trying to draw the complementary handle body as a standard handle body. Maybe I'll drop the blue altogether. Right? I'm trying to draw the complementary handle body as a standard handle body, and I'm trying to let. This sort of picture is a little bit bad. I prefer this picture where I have just, see, when you see it this way, you think there are 3 handles, right? Okay, actually, and so it's going to go, so this picture, for this picture, right, just draw a handle here, and a handle here, and what I know is each handle I have 4 strands going over it, right?
Green now?
But already you can sort of anticipate potential problems now because you've got 4 strands going up each handle. It doesn't mean it's not going to work.
There's different ways to connect it.
There's different ways to connect them up once you get down here. So now this is what we have to figure out carefully, is how they're connected up and down on the surface. Does everyone agree that there are 4? My argument for why there are 4 is if you go from the front to the back, this goes back once, and here this goes from front to back once, this goes from front to back once, and then this goes from front to back once. So there's 4 things. It's symmetric on the other side. So what we really want to try to visualize is I know the right thing to do here is, the right thing to do is to flip this strand over. That'll help a lot in this picture. That was the trick that what the trick is to get the cipher surface you start with passing through infinity. That's what we did before. The initial cipher surface, you're going to work with a complement of one cipher surface. So if we flip this around, so start. Now the red cipher surface outside. Completely. And here. And so now it's a little bit, might be a little bit easier to see because the blue, the handle body here is this is the connector to that ball.
There's the ball.
There's your ball. Okay. We were showing the ball. Okay. Right. And then there's your ball, and now we've got a handle going through here and a handle going through here. It's a little bit, we like as much of it as possible to be on the ball. It goes through.
But it's flat again.
Right.
So you can draw the little twisted strips. Is that what you want to do?
What I want to do is I want to see, here's a ball, here's a handle that goes through there, here's a handle that goes through there, okay? And everything's running, so everything's sitting on the boundary of that, the ball. Really, I sort of imagine this, the way I imagine it is, here's the ball, and it's really more sort of like a, something like that, okay? And then I've got, inside here, I've got a handle inside there, going through there and one through there, connecting these two sides. Okay, and then I've got this whole thing sitting on, so there's a ball that's really concavity in here, and then a handle through there, and everything's sitting on there. And just think I'm flooding it and forcing out of time, so it's an inelegant way to end the thing. We'll start, I promise to have this carefully sorted out, but you can also think about on the weekend. How do you draw that here, right? And then we're going to actually take this example, and first of all, we see that the cutting open argument leads to some kind of problem, right? And then we're going to try to actually find a way to see the scribblers isn't built out of handles, and then see if we can actually compute the Morse homology to show that there isn't some weird way to do it. Because of course, if we just cut here and cut here, right, and we don't get one component, that doesn't mean we couldn't cut in some other way, right? Okay. Or maybe pick a different cipher surface. That's the other point, is that we don't know. You might have picked the wrong cipher surface, and that's why it doesn't seem like it's working with fiber. So there are lots of cipher surfaces for you. Okay. Sorry for that.
So what's the abstraction here? Because just
The
because
abstraction is going to be the more smaller g.
yeah, but what about it? Like
That
just
it's not
being
zero.
non-trivial?
Yeah.
Okay, so it has to be.
It has to be 0 in order to be fiber.
I see. Because if it's fiber, it has no critical points. There's no generators.
Exactly.
Even second. So it's sort of the
Right.
same story.
Exactly.
You know.
Yeah.
Because all this weirdness in the algebra comes from if you have generators.
That's right.
Then there's
Exactly.
then flow lines can do weird things. If you don't have generators, then
And there's nothing.
there's nothing weird going on.
It's very easy to compute.